I am going to introduce a course on optimization methods. Do you know that you can optimize your proposals by using optimization methods? Do you know that optimization methods impose constraints that are considered necessary and eliminate solutions that fail to satisfy these constraints? Do you know that there are very powerful software programs such as GAMS that solve optimization problems for you? If you want to incorporate optimization methods to your way of facing problems and acquire new solving problems power, I invite you to this course that will reveal you wonderful ideas and tools that you never thought about and will surprise you. Optimization methods are very important and useful because first, they force constraints to be satisfied, which is relevant in engineering, mainly in safety analysis. Second, because they optimize the solution, that is, they allow us to select the best solutions. Third, because they allow us to perform a sensitivity analysis very easily, which tells us how the solution changes when data changes. And finally, because they are very good software available, such as GAMS, to solve these problems. This course is about optimization methods and includes a description of the GAMS code and a detailed analysis of the sensitivity problem. I invite you not only to learn how to use optimization methods, but mainly to incorporate them to your way of solving problems in engineering, physics, and mathematics. The aims of the course are the following. First, I want to emphasize the power of optimization methods. Optimization methods permit solving practically any problem you can imagine. Second, I want to encourage model building through optimization methods. I would like the students to incorporate optimization methods as one possibility for solving the problems they face. Third, I want to help to identify the main elements in an optimization problem. They are data, variables, restrictions, and objective function. This is not easy at the beginning, but this course will help you to do that. I also want to teach how to use GAMS to solve the vast majority of the optimization problems. I want also to present different applications to motivate many others, especially those related to each student area. I want to show that GAMS allows to separate theory from practice, letting theoretical experts focus on the aspect of mathematical and programming rigor and experts applied in the modeling and validation of problems. And finally, I want to introduce sensitivity analysis and associated tools. What we will see in this course? The main topics of this course are linear programming, nonlinear programming, mixed integer programming problems, duality in mathematical programming, sensitivity analysis, and finally, some examples of real applications that illustrate all the theory. For example, in the case of linear programming, we introduce this linear programming with some examples. For example, the transportation problem that assumes that you have some things to be transported from some origins to given destinations, and you need to choose the amounts to be obtained from each place in order to minimize the cost of transportation. Another problem will be the production scheduling problem, in which you have to satisfy a demand, and then you have two options, either to adjust the scheduling fabrication to the demand, or you prefer to have a constant demand and use some stock material just to cover from the deficits in some periods. Another problem is the diet problem, in which you have to determine the amounts of different nutrients that must be used to minimize the cost and satisfy some nutrition conditions. I will describe in this course to you the 4 types of problems you can face. The most common problem you will face is the problem with unique solution. Then the software will give you that unique solution, and you have normally you won't have any problem. The second type of problem is a problem in which you have multiple solutions, normally infinitely many, and the software will give you only one. That is a problem because in some cases you will like to know all the possible solutions. However, we will make an effort in order to obtain all possible solutions when possible. Another problem is when you have an unbounded problem, and that means that the problem is not well stated. You need more constraints such that you avoid abundance. And finally, you have problems in which there is no solution at all. So you have a problem with which is unfeasible. And that is because some constraints contradict other constraints, so that no possible solution can satisfy all of them. We will dedicate some time to the simplest algorithm. The simplest method is the most well-known method in mathematical programming. It has been used for many years and it works very nicely. It has been tested, and what we will do is the following. We want to transform our problem to a particular form such that you immediately are able to say the solution without any calculations. If you have an objective function that has the structure of a constant plus linear combination of non-basic unknowns or non-basic variables, and the constraints are written in the form that the basic variables are a constant plus linear combination of the non-basic variables, in that special case, you can solve the problem immediately. Let me first tell you what basic and non-basic variables are. In a linear programming problem, you have variables, and then you have to divide the variables in 2 groups. One is the basic and another is the non-basic variables. The basic variables are those variables that are written as a constant plus linear combination of other variables, and the non-basic variables are those variables that cannot be written in such a way. But look, if your objective function is a constant plus linear non-negative combination of non-basic variables, non-negative linear combinations, and the basic variables can be written as non-negative constant plus linear combinations on non-basic variables, in that case, we can say that the solution of this system that is subject to non-negativeness of the solution is always obtained for values of the non-basic variables equal to 0 and for the basic variables equal to the constants in the corresponding expressions. So the idea is we have a linear programming problem, we write the linear programming problem in this form, and probably we are not able at the beginning to obtain the basic variables as non-negative constant plus the combination of the non-basic variables, but some of this constant is negative. In addition, the objective function probably is difficult to be written at the beginning using non-negative combination of non-basic variables. So what we do is we start with a problem that is written in the convenient form, separating the non-basic and the basic variables, but don't satisfy that condition. Then what we do is first in one step, because this can be done in one step, we can transform all the constants in the expressions of the basis variables to non-negative values. This is in one step. And later, we can, maintaining this condition, we can change the coefficients of the objective function to positive values in different iterations. And this is what the simplest method does. So we will describe a regulating iteration in which we obtain positiveness in the basic variables expressions, and in a standard iteration, in several standard iterations, we will get positiveness in the objective function. And finally, we will explain to you how to detect unboundedness when the problem is unbounded, and how to detect infeasibility when the problem is infeasible. And this will complete an idea of the simplest algorithm. With the nonlinear programming problems, we will introduce then by some examples. First, we will deal with the 10 problem. You are required to build a 10 using the minimum cost possible, but the 10 has to be a given geometry and some constraints to be satisfied. Next, we will deal with the postal package, in which the postal company puts some conditions for the packages, for the sizes of the package that you can use. And you need to design a package that leads to the minimal cost of transportation. In other words, that gives you the maximum volume, because the postal company only will charge you for trip. Another possibility is the case of the moving sun example, in which you have to design a box to transport a given amount of sand. The problem here is that you need to build a box. If the box is very big, it will cost you a lot of money, but because you are the price of the transportation is $2 per trip, independently of the size of the box. The problem is that you need to balance the cost of building the box with the cost of transportation, and that is what this example explains or forces. The next example is the following. You are supposed to simulate random points, and then once you have simulated these random points, you need to find the minimum size circle that contains all the points inside or at the boundary. It is interesting to see that the solution will contain 3 points at the circumference and the rest inside, unless there is a degeneration. And it is important because 3 points define a circle. So this is an interesting example. And another example we will treat with is the case of a transportation network, and you are interested in knowing the transportation time for each of the links. You want to know the minimum travel time from every pair of nodes. At the end of this nonlinear path, we will discuss and we will add some theory just to know the necessary and sufficient conditions for optimality. Because we want the student to be able to use the GAMS code, we will describe some general rules for GAMS and also some commands. At the beginning, we will describe some commands for defining the data as sets, scalars, parameters, and tables. We will describe the variable commands to define the variables. We will define the equations commands to define the constraints and the objective function, and we will study the model and solve commands to define a model and to solve it, and finally the display commands to explain how to get the result of our problems. An interesting part of the course will be the Karuskand-Tucker conditions. which gives you the necessary conditions for having an optimal value. Probably you are familiar with the case of optimization method in which you have no constraints, and you know that the partial derivative of the objective function made equal to 0 gives you a system of equations that gives you the optimal solution. You probably are familiar with the case of equality constraints in which you use the Lagrangian, and we obtain partial derivative of the Lagrangian to obtain the system of solutions. But probably you don't know what to do with inequalities. And Karius-Kanthacker conditions will explain you what are the conditions that need to be used to solve problems with inequalities. We'll illustrate the Karius-Kanthacker condition with graphical interesting interpretations of these conditions. And we will also solve some examples, and we will interpret the different constraints for you to be familiar with Karius-Kanthacker conditions. And finally, we will study the case of convex functions and concave functions and discuss the sufficient and necessary condition for minimum. In the case of the mixed integer programming problems, we use some interesting examples as the Knack-Schaap problem or the ship owner problem. We will also use an example of identifying relevant symptoms. We want to diagnose different diseases, and we have a set of symptoms. And we want to decide the minimum number of symptoms that we need to use to differentiate the different diseases at different levels. It is an interesting example that can be solved with mixed integer programming. Another problem is the academy problem, in which we solve a problem in which we want to select new academicians, and there was a previous test and some information was lost, and we want to recover that lost information, not completely but partially, in order to make some decisions. It is an interesting problem in which when you lose information, you can recover, in some cases, all the information, but in some cases, only one part, but very relevant part. And also, we will discuss the timetable, school timetable problem, in which we have to distribute rooms to teach different courses with different professors and with different topics. And we will also discuss the problem of location of different facilities in order to satisfy the demand, and we need to choose where to install the factories in order to get the maximum benefit of our investment. It is very interesting to see the general structure of the solutions of the system of inequalities, and you can see that it is a polyhedron that is the sum of a linear space plus a cone plus a polytope. This is very important because if we know the mathematical structure, we know what we need to look for in order to define and to know all the solutions. And also we have to see what happened in the case of homogeneous system of equations, in which case we have linear subspaces. What happened in the case of complete linear system of equations, in which case we have affine spaces with, we need to determine one particular solution and a linear subspace. What to do with homogeneous system of inequalities? The solution is a cone. In the case of complete linear system of inequalities, we have a polyhedron. And finally, in the case of bounded complete linear system of inequalities, in which case we have a polytope. It is very important to know that in engineering, because in many cases we have bounded solutions, cones and linear spaces are not possible, and we are led to the case of polytopes. You will be given a table in which you have a full description of all this for you to understand this. And then we will move to duality. We will explain that given a linear programming problem, there exists a dual problem associated to it, which is its dual. We will explain the definition of dual problem. We will explain different rules in order you to obtain, given a particular case of linear programming problem, how to obtain its dual very easily. And we will illustrate this with some examples. In particular, we will use a table manufacturing example and also a support vector machine example, which is using artificial intelligence. And even in this case, we will use the dual of the primal problem, and we will give an interpretation to the dual, which is even more interesting. Of course, we will discuss the duality theorems for this case and the weak duality theorem that gives the relation between the primal and the dual problems. And we also illustrate the saddle point property that we obtain in this type of problems. One example that has special relevance is the case of the electric market. In this case, you have different producers that compete in the market. All of them produce electricity that cannot be stored. It has to be produced and immediately consumed. And the problem is that they need to decide how much electricity to produce each of the producers. So they have a system operator that can act in two different ways. The first way is the centralized of primal approach, in which the system operator asks the producers about all private information. That is not good for them because they want to reveal this private information. And even the operator, taking all this information, decides what is the amount of electricity to produce each producer, and forces them to produce such an amount without participating in the decision. This is understood as a dictatorship because they impose the production. The second approach, which is the dual, in this approach, the producers are given the prices they will receive for each production, and they decide how much to produce without revealing the private information to anybody. And they decide freely the amount to be produced. And the regulator has only the possibility of changing prices, so that the prices are changes until there is an equilibrium and the demand is satisfied. And the curious thing is that the final result for the primal and the dual problem is the same. So you can appear as a dictator or a democrat depending on how to act. If you decide the production, you are a dictator. If you decide only the prices, you are a democrat. And that is a very interesting example to this. Another interesting thing to deal in this problem is sensitivity analysis. We need to give the result of the optimal solution, but also it's nice to explain the user how much the optimal solution changes when you change the data. We will apply this to several civil engineer examples, a bridge crane design, to the case of a vertical breakwater, or to a retaining wall example. And we will ask different questions about sensitivity. For example, the first question we can ask is what are the local sensitivities of the objective function when we change the data, the A, B, or C in that example. We can also ask what are the local sensitivities of the primal variables to change in the data. Or even we can ask what are the local sensitivities of the dual variables to change in the data. So we are interested in the sensitivities of the objective function, of the primal, of the dual. We want to know what is the change that we have in the objective function, in the primal, or in the dual variables when you change the data. And first we will give a very interesting theorem that gives you the sensitivities of the objective function with respect to any parameter. We will see that the partial derivative of the Lagrangian function gives you this sensitivity. This is a very interesting result that is not very well known, that you will know in this course. We know the meaning of the dual variable. We know that the dual variables gives you the sensitivity of the objective function value when we change the right-hand side terms of the constraints. This is well known. So we can use a trick and we can change our programming problem, including fictitious constraints that simply convert your parameters into a new variable, but then you force the variable to be a particular value. So with this trick, you can use this property and use the corresponding dual variable to obtain the sensibilities. But we go even further. We are going to perturb all the Karus-Kantaker conditions one by one, and we are going to obtain at the end a system, closed formulas for all sensitivities at once. And we will give some examples. In particular, if you apply these formulas to the case of linear programming, you will have formulas for all possible sensitivities in linear programming. And some of these formulas are not known. Some they are new, and you can discover the importance of these formulas. Finally, we want to apply this to the engineering examples of the vertical breakwater, and you will see how to do that. We will apply this to the case of a neural network. We want to learn the network, even the weights, and also in some cases we want to learn the neural functions. We will use 5 different models and we will compare them, which is very interesting because in some cases we approximate the neural function, we use the neural function, and in other cases we use the inverse of the neural function, which is much simpler, but it's equivalent. And then we will compare with one example and see the effect. And finally, we deal with regression models. In the case of regression, we study the least squares regressions, in which case the solution passes through the center of gravity. It is nice, it is incredible that many users don't know that the least squares regression passes through the center of gravity, and you can see examples in which this is not satisfied, so that means that the problem is wrong. In the case of the minimax regression, it is interesting to see that only 3 data points define the solution, and this is nice because even we can solve the problem graphically. In the course, I will explain you how to obtain the solution of the minimax problem graphically. And finally, you have the least absolute value regression, in which the solution should pass through 2 of the data points. This is another fact that is not known by the people, and you will learn about this beautiful result that will help you to understand regression. And finally, and this is really the final, my final, is that we are going to use an example, a regression example, in which we add artificial outliers. We are going to use all these methods and we are going to compare them, and you will see what are the advantages of one or another method to be used in each case. And this is the end of my summary about this course. You have seen how to build an optimization problem, identifying and selecting the data, the variables, constraints, and the objective function. You already know that GAMS helps you to solve the problem. You also know that you can inform the client not only about the optimal solution of the problem, but on the sensitivity analysis that you can perform. Finally, if you want, you can obtain the dual problem and give it a physical interpretation to gain a deeper knowledge about your problem. You are invited to follow this free course.